So thank you very much for giving me the opportunity to share the work we have done recently based on the high resolution ensemble uncertainty using generative diffusion based machine learning model. So this I am Swapan Mallick from Swedish Meteorology and Hydrology Department, and this work actually done with the collaboration of different institute and under Copernicus reanalysis group. So from like Swedish Meteorology and Hydrology and Met Norway and Danish Meteorological Institute. So the outline of my talk is using the Copernicus Arctic regional reanalysis, which provides a high resolution like 2.5 kilometer atmospheric data uh, to improve the orography and regional process compared to the coarser resolution like ERA 5 data. And it covers over the Pan-Arctic region. It uses 3D bar data assimilation for production. But for the main goal of this work research is to develop a empirical relation using the generative diffusion based machine learning approach, combining both ERA 5 EDA and Kara 2 and Kara 2 data. Hello.
Yeah, we hear you.
Okay, sorry. So in this research, we developed a generative machine learning diffusion model, and the result shows that the generative diffusion model is able to capture the high resolution Kara2 data and the orographical flow dependent uncertainty. And in my this future task, we use code-based data simulation. So I'll show some slide on this. So as I mentioned, background of this work is based on the Kara2 second generation reanalysis data, which is quite a large domain and very high resolution data, which is 2.5 kilometer, having vertical level 65, and it used 3D bar data assimilation system. Now, since we use 3D bar data assimilation system and the B matrix is based on the background climatological background V matrix. So for that, we need to prepare the ensemble data set to calculate the B matrix. And that, so there we used 10 ensemble member from ERA 5 EDA to generate the Kara2 ensemble data assimilation. And this is the B matrix structure and how here I am showing how the B matrix differ from the different season, winter and summer season, and what is the importance of B matrix. Now coming to the uncertainty, this when we calculate the ensemble member for Kara2 data, we have seen that lot of huge uncertainty over the different part of the area and specifically over the coastal part of the Greenland and uh, over the Canada region. So there is a flow dependent uncertainty has been observed in the Kara2 ensemble system. So now the goal is to find the relation between the ERA 5 EDA and Kara2 uncertainty. So for that we use the generative diffusion model, and basically the generative diffusion model is a very new system and it has a different flavor like denoising diffusion probabilistic model and score-based diffusion model. So, and the foundation model is the denoising diffusion model, which is very recently introduced, and it's fully based on the Markov chain process, and it learns the it pulls the noise at different step, and from in reverse process it learns the noise the difference. Whereas the score-based diffusion model is based on the gradient of the data distribution, which actually calculate the direction of the flow of the error. So, uh, so we first consider the denoising diffusion probabilistic model, and here we use the ERA 5 EDA as an input ensemble, and Kara 2 is the target. So this figure shows that the how denoising diffusion probabilistic model works. It's a schematic representation of the uncertainty. So basically, we are using the in forward process. We are using the data, and for each step, it added some noise, and finally, the final stage is a fully Gaussian noise, and in reverse process, it calculate the noise distribution, and from the and it will generate the actual data. So for that, it's a very expensive process, and in our system we use total 4,000 noise step, and UNet is the main brain of the diffusion model. So we use the UNet structure for that. And here how the uh, forward process works in denoising diffusion system, it's showing, and the reverse process it calculate the distribution of the distribution of the data from previous step. And this is the flowchart of the data what we use. So basically, for any machine learning model, we know that we need a huge data set. But for this work, we didn't use so much data set. It's we use for training only uh, like 6-month data set, because we have a 10 ensemble member, and each day we have 4 UTC from 0006, 12, and 18 UTC. So we use 90% data for training and 5% for validation. For any machine learning model, we know that the data pre-processing is a huge challenge, and it takes a lot of time. So what we have done, like we use the ERA 5 EDA, first downloaded those in either GRIB and SCDF, then we convert all the data in a ZAR format, and then we use that Kara 2 as a target, and ERA 5 EDA is the condition. And then we run the training model using denoising diffusion probabilistic model. And for evaluation and validation, we use only the ERA 5 EDA, and it produces the uncertainty as well as the field also. So this is the flowchart of the training supervised diffusion model, what we did. So here we can see that the ERA 5 EDA is the condition, standard deviation, and the ensemble mean. For suppose if we consider 2-meter temperature ensemble, and the target is the Kara 2, where Kara 2 is the ensemble uncertainty, and this is actually deterministic forecast, the field which come from the high resolution analysis field. And then we train the model in supervised way. And for evaluation and validation, we use the ERA to ERA 5 EDA uncertainty and ensemble mean with the model output, and it generates the uncertainty, flow dependent uncertainty, and also the deterministic field with high resolution. So it should be noted that this ERA 5 EDA input is the very coarser resolution, which is 62 kilometer resolution, whereas the CARA 2 is 2.5 kilometer resolution. So in this methodology, we implement two tasks. One is for downscaling and one is for predicting the uncertainty and field. So this figure shows that the 2-meter temperature uncertainty, it's some kind of climatological uncertainty over the whole year. So it generates the ensemble uncertainty over the whole period for using the different training output. So we can see that the most of the uncertainty over the coastal part, coastal area, like over the Greenland and the Canada region and other places. So, but it's not a constant; it's a fully flow dependent, and it also captures the orographical structure of the uncertainty. So for evaluation and validation, how we did those, how we calculated that uncertainty is fully based on the training model output. So for we train model like 50,000 time step, and for each time step we save those model, and then for sampling we extract the information from the different model and calculate the uncertainty, how for each model able to capture the uncertainty. Then based on the root mean square error and the mean square error and score function, we calculate we uh, created the same ensemble for the uncertainty over the specific time. So this is one example for validation for a particular time at a different UTC. So ERA 5 EDA is the input, and CARA 2 is not used in the training model. It is just for a validation to see how the flow dependent works. And these two are the model output, DDPM model output is a maximum uncertainty and minimum uncertainty and maximum uncertainty. So it generates the similar kind of flow for uncertainty over the area. And we can also see that it's not, uncertainty is not a fixed, it's a very flow dependent. For different UTC, uncertainty varies slightly. And for field evaluation, for 2-meter temperature to generate the actual field, we also use the similar method. And for each model output, we can see that different um, different field is generated for 2-meter temperature. And we suppose if we consider the threshold value is 0.03 mean square error. So we took this is the maximum threshold value, and if the root mean square error is less than those threshold value, and then we took the ensemble member. This is another example for this 2-meter temperature calculation. So ERA 5 EDA is the input, and CARA 2 is the validation, and how the diffusion model generate the field. Here we can see that it's very similar over the region, over the area. Although some kind of biases are there, since in this model we didn't use any observation. It's directly from the ERA 5 EDA. So we can expect some kind of systematic bias, but it's very flow is The Ensemble member shows is very promising result. And this is for a specific time for 2-meter temperature validation. So here era 5 is the input, and Kara 2 we use for comparison, and the generative model output is this figure. Sorry. And this is another example for surface pressure. It's we can see that the era 5 EDA is a very coarse resolution, and it generate the similar feature for
2
Kara
minutes
2.
left.
Yeah. So the DDPM or generative model able to capture the similar features. Okay, this is another example for the machine learning generated uncertainty and the field also. So this is the whole work is done under the Copernicus region, Copernicus framework, and the full report is available in this website if someone is interested to see the details of that report. Coming to the summary, so we have seen that the denoising diffusion probabilistic model able to capture the uncertainty based on the orographical structure and also flow dependent uncertainty, and it's also able to capture able to downscale them from coarser resolution and high resolution. So the now next step is to use the actual observation, which is based on the score based diffusion model. And this work we just started recently for using score-based data assimilation. So here, since the SCADA has a very less ensemble member we generated, and it's very expensive. So here we are testing with the SERA reanalysis data for 40 years. Data is available. So basically, score-based data simulation is one of the good way to implement the actual observation over the location, and this work is in process. So yeah, I am not going to the details of the how we know that the classical method data simulation method, but the score-based actually it calculates the direction of the error, and it's very suitable for the data simulation method. Yeah, thank you very much for this, giving me the time for the opportunity. This is my last slide.
Thank you for your talk, Swapan. It was very interesting. I enjoyed it. The questions, it doesn't look like we have any questions on the OPAD, but if anybody has any, feel free to write them down, and I'm sure Swapan can go and take a look afterwards. So I guess I think James wants to close, so I'll pass